Welcome back. Let's try continuous reading. It's very hot in my apartment. Like always, it's 30 degrees always. I did finish my Danish video about mechanical calculators. This mechanical calculators. Then I like to read all this, and let's just start it. Could try finish like tomorrow evening or 2 days. So I will just go to bed, follow my list, then I will read one by one. It's about different kind of old mechanical calculators.
Napiers bones. This article has multiple issues. Please help improve it or discuss these issues on the talk page. Learn how and when to remove these template messages. Napiers bones is a manually operated calculating device created by John Napier of Merchiston, Scotland for the calculation of products and quotients of numbers. The method was based on lattice multiplication, and also called rhodology, a word invented by Napier. Napier published his version in 1617. It was printed in Edinburgh and dedicated to his patron Alexander Seton. Using the multiplication tables embedded in the rods, multiplication can be reduced to addition operations and division to subtractions. Advanced use of the rods can extract square roots. Napier's bones are not the same as logarithms, with which Napier's name is also associated, but are based on dissected multiplication tables. The complete device usually includes a baseboard with a rim. The user places Napier's rods and the rim to conduct multiplication or division. The board's left edge is divided into 9 squares, holding the numbers 1 to 9. In Napier's original design, the rods are made of metal, wood or ivory and have a square cross-section. Each rod is engraved with a multiplication table on each of the 4 faces. In some later designs, the rods are flat and have 2 tables or only one engraved on them, and made of plastic or heavy cardboard. A set of such bones might be enclosed in a carrying case. A rod's face is marked with 9 squares. Each square except the top is divided into 2 halves by a diagonal line from the bottom left corner to the top right. The squares contain a simple multiplication table. The first holds a single digit, which Napier called the single. The others hold the multiples of the single, namely twice the single, 3 times the single and so on up to the 9th square containing 9 times the number in the top square. Single-digit numbers are written in the bottom right triangle leaving the other triangle blank, while double-digit numbers are written with a digit on either side of the diagonal. If the tables are held on single-sided rods, 40 rods are needed in order to multiply 4-digit numbers since numbers may have repeated digits. 4 copies of the multiplication table for each of the digits 0 to 9 are needed. If square rods are used, the 40 multiplication tables can be inscribed on 10 rods. Napier gave details of a scheme for arranging the tables so that no rod has 2 copies of the same table, enabling every possible 4-digit number to be represented by 4 of the 10 rods. A set of 20 rods, consisting of 2 identical copies of Napier's 10 rods, allows calculation with numbers of up to 8 digits, and a set of 30 rods can be used for 12-digit numbers. Multiplication, edit. The simplest sort of multiplication, A number with multiple digits by a number with a single digit is done by placing rods representing the multi-digit number in the frame against the left edge. The answer is read off the row corresponding to the single-digit number which is marked on the left of the frame, with a small amount of addition required, as explained in the examples below. When multiplying a multi-digit number by another multi-digit number, the larger number is set up on the rods in the frame. An intermediate result is produced by the device for multiplication by each of the digits of the smaller number. These are written down and the final result is calculated by pen and paper. To demonstrate how to use Napier's bones for multiplication, 3 examples of increasing difficulty are explained below. Multiplication by a small single-digit number, edit. The first example computes 425/6. Napier's bones for 4, 2, and 5 are placed into the board, in sequence. These bones show the larger figure which will be multiplied. The numbers lower in each column, or bone, are the digits found by ordinary multiplication tables for the corresponding integer, positioned above and below a diagonal line. For example, the digits shown in the 7th row of the 4 bone are 2, 8, representing 7, 4 equals 28. In the example below for 425/6, the bones are here depicted as red, 4, yellow, 2, and blue, 5. The leftmost column, preceding the bones shown colored, may represent the 1 bone. A blank space or 0 to the upper left of each digit, separated by a diagonal line, should be understood, since 1, 1 equals 0, 1, 1, 2 equals 0, 2, 1x3 equals 0, 3, etc. A small number is chosen, usually 2 through 9, by which to multiply the large number. In this example, the small number by which to multiply the larger is 6. The horizontal row in which this number stands is the only row needed to perform the remaining calculations and may now be viewed in isolation. For the calculation, the digits separated by vertical lines, i.e. paired between diagonal lines, crossing over from one bone to the next, are added together to form the digits of the product. The final, rightmost, number on that row will never require addition, as it is always isolated by the last diagonal line, and will always be the final digit of the product. In this example, there are 4 digits, since there are 4 groups of bone values lying between diagonal lines. The product's digits will stand in the order as calculated left to right. Apart from the first and the final digit, the product's digits will each be the sum of 2 values taken from 2 different bones. Bone values are added together, as described above, to find the digits of the product. In this diagram, the third product digit from the yellow and blue bones have their relevant values colored green. Each sum is written in the space below. The sequence of the summations from left to right produces the figure of 2550. Therefore, the solution to multiplying 425 by 6 is 2550. Multiplication by a larger single-digit number, edit. When multiplying by larger single digits, it is common that upon adding a diagonal column, the sum of the numbers results in a number that is 10 or greater. The second example computes 6785/8. Like example 1, the corresponding bones to the biggest number are placed in the board. For this example, bones 6, 7, 8, and 5 were placed in the proper order as shown below. In the first column, the number by which the biggest number is multiplied by is located. In this example, the number was 8. Only row 8 will be used for the remaining calculations, so the rest of the board has been cleared for clarity in explaining the remaining steps. Just as before, each diagonal column is evaluated, starting at the right side. If the sum of a diagonal column equals 10 or greater, the tens place of this sum must be carried over and added along with the numbers in the adjacent left column as demonstrated below. After each diagonal column is evaluated, the calculated numbers are read from left to right to produce a final answer. In this example, 54,280 was produced. Therefore, the solution to multiplying 6,785 by 8 is 54,280. Multiplication by a multi-digit number, edit. The third example computes 825,913. The corresponding bones to the leading number are placed in the board. For this example, the bones 8, 2, and 5 were placed in the proper order as shown below. To multiply by a multi-digit number, multiple rows are reviewed. For this example, the rows 4, 9, 1, and 3 have been removed from the board for clarity. Each row is evaluated individually and each diagonal column is added as explained in the previous examples. The sums are read from left to right, producing the numbers needed for the longhand addition calculations to follow. For this example, row 9, row 1, and row 3 were evaluated separately to produce the results shown below. Starting with the rightmost digit of the second number, the sums are placed from the rows in sequential order as seen from right to left under each other while utilizing a 0 for a placeholder. 2,475, 8,250, 742,500. The rows and placeholders are summed to produce a final answer. 2,475, 8,250, plus 742,500, 753,225. In this example, the final answer produced was 753,225. Therefore, the solution to multiplying 825 by 913 is 753,225. Division, edit. Division is performed in a similar fashion. To divide 46785,399 by 96,431, the bars for the divisor, 96,431, are placed on the board, as shown in the graphic below. Using the abacus, all the products of the divisor from 1 to 9 are found by reading the displayed numbers. Note that the dividend has 8 digits, whereas the partial products, save for the first one, all have 6. So the final 2 digits of 46785,399, namely the 99, are temporarily ignored, leaving the number 467,853. Then, the greatest partial product that is less than the truncated dividend is found. In this case, 385,724. Two things must be marked down, as seen in the diagram, since 385,724 is in the 4 row of the abacus. A4 is marked down as the leftmost digit of the quotient. The partial product, left aligned, under the original dividend, is also written. The two terms are subtracted, which leaves 8212,999. The same steps are repeated. The number is truncated to 6 digits. The partial product immediately less than the truncated number is chosen. The round number is written as the next digit of the quotient, and the partial product is subtracted from the difference found in the first repetition. The process is shown in the diagram. The cycle is repeated until the result of subtraction is less than the divisor. The number left is the remainder. So in this example, what remains is a quotient of 485 with a remainder of 16,364. The process usually stops here and the answer uses the fractional form 485. plus 16,364 / 96,431. For more accuracy, the cycle is continued to find as many decimal places required. A decimal point is marked after the last digit of the quotient and a 0 is appended to the remainder, which leaves 163,640. The cycle is continued, each time appending a 0 to the result after the subtraction. Extracting square roots, edit. For extracting the square root, an additional bone is used which is different from the others as it has 3 columns. The first column has the first 9 square numbers, the second has the first 9 even numbers, and the last has the numbers 1 to 9. Napier's rods with the square root bone. 1 2 3 4 5 6 7 8 9 square root. 1 0 1 0 2 0 3 0 4 0 5 0 6 0 7 0 8 0 9 0 1 2 1. 2 0 2 0 4 0 6 0 8 1 0 1 2 1 4 1 6 1 8 0 4 4 2. 3 0 3 0 6 0 9 1 2 1 5 1 8 2 1 2 4 2 7 0 9 6 3. 4 0 4 0 8 1 2 1 6 2 0 2 4 2 8 3 2 3 6 1 6 8 4. 5 0 5 1 0 1 5 2 0 2 5 3 0 3 5 4 0 4 5 2 5 10 5. 6 0 6 1 2 1 8 2 4 3 0 3 6 4 2 4 8 5 4 3 6 12 6. 7 0 7 1 4 2 1 2 8 3 5 4 2 4 9 5 6 6 3 4 9 14 7. 8 0 8 1 6 2 4 3 2 4 0 4 8 5 6 6 4 7 2 6 4 16 8. 9 0 9 1 8 2 7 3 6 4 5 5 4 6 3 7 2 8 1 8 1 18 9. To find the square root of 4 6 7 8 5 3 9 9, its digits are grouped into 2 starting from the right, so it looks like this. 4 6 7 8 5 3 9 9. Note, a number with an odd number of digits like 85,399 would be grouped as 085399. The leftmost group is chosen first, in this case 46. The largest square on the square root bone less than 46 is picked, which is 36 from the 6th row. The first digit of the solution is 6, since the 6th row was chosen. Then, the number in the second column from the 6th row on the square root bone, 12, is set on the board. The value in the first column of the 6th row, 36, is subtracted from 46, which leaves 10. The next group of digits, 78, is added next to 10. This leaves the remainder 1078. At this stage, the board and intermediate calculations should look like this. 1 2 square root. 1 0 1 0 2 0 1 2 1. 2 0 2 0 4 0 4 4 2. 3 0 3 0 6 0 9 6 3. 4 0 4 0 8 1 6 8 4. 5 0 5 1 0 2 5 10 5. 6 0 6 1 2 3 6 12 6. 7 0 7 1 4 4 9 14 7. 8 0 8 1 6 6 4 16 8. 9 0 9 1 8 8 1 18 9. Square root 46 78 53 99 equals 6. 36. 1078. The numbers in each row are read, ignoring the second and third columns from the square root bone. These are recorded. For example, the 6th row is read as 061236756. Like in multiplication shown before, the numbers are read from right to left and add the diagonal numbers from top right to left bottom. 6 plus 0 equals 6. 3 plus 2 equals 5. 1 plus 6 equals 7. The largest number less than the current remainder, 1078, from the 8th row, is found. 1 2 square root, value 101020121121, 2020